Welcome. My name is Rob Alley, and I'm an engineer with Elrod Engineering. Our company has been providing sign design and structural engineering services since the 1980s, and we're proud to be a longtime member of Mid-South Sign Association. Thankful for this opportunity to share with you a bit about the engineering side of your signage and architectural element world. Appreciate you spending this next hour as hopefully I give you a helpful overview of what goes into the sign engineering for freestanding and existing signs. I certainly don't intend to make an engineer out of you, but it's been our experience that if you as a project manager have a good basic understanding of what goes into the design of a sign, you'll first off have a smoother working relationship with your engineer, and more importantly, be able to better serve your client. Hopefully, we'll have some time for questions at the end. We do have a lot to cover, so let's dive in. In the first session, we spent a little bit of time working towards a general understanding of engineering principles, some of those fundamental underlying concepts. We'll touch on some of those today, but our focus is shifting to more specific sign types, in this case, freestanding signs. So, 2 weeks ago, we talked about sign engineering in general and wall signs. Specifically today, we'll get into freestanding signs, what makes a good sign order, and existing sign structure inspections. This last topic is something that's increasingly becoming important to our clients and comes up more and more. So we've got a good format and wanted to share that with you. But first, a refresher on sign engineering concepts. Two main topics that we're going to review are basically theory and practice. The theory is what drives the design, things like building code, risk category, and design loads. And then the practice side, what information does your engineer need and what makes a good sign request? So the building code basically tells us what and how loads are applied to a sign structure. Even though it is city and state dependent, it can vary widely across a region. I like to give the example of Texas. Across the state of Texas, it ranges from the default statewide building code of the 2003 version of the IBC to the 2001 or 2021 version in several cities. That is the most current version. Several states have a state-specific code. It may simply incorporate a particular IBC by reference, such as North Carolina, or it may be pretty unique, such as Florida and California. Some cities do have a specific building code, like the previous version of Chicago, even though that's very uncommon. And then I always like to remind people about Disney World. Disney World has the Epcot building code, which not only covers signage in the Magic Kingdom, but also roller coasters, haunted houses, and other things that you would never have dreamed of. So why does this matter to you? Basically, a sign that you build in one city may not be properly designed for a nearby city. The most stark example of this is where the 2009 building code is still in play versus the 2012 version. Very different analytical approach, and so you actually get slightly different results. And so what is per codes in a 2009 IBC city may not meet codes in 2012. Surprisingly, cities often do not view codes as backwardly compatible. For example, you would think that if you designed a sign to the 2021 version of the building code, it would be applicable everywhere. But if the city has adopted a 2015 version, they will not accept calculations or drawings that are done per the 2021 building code and identified as such. This information about the building code is particularly important for your clients who may have a pre-designed family of signs that are installed across a large region or even nationally. Each building code references a specific ASCE design manual for what and how loads are applied. The building code could be thought of as the what, and in many ways, this design manual prepared by the American Society of Civil Engineers is the how. So it tells the engineer how to do the analysis, how to apply the loads that are required by the building code. Two factors that arguably have the most impact on design loads are the risk category and the exposure category. The risk category, ranked 1 through 4, basically describes the use of a structure and how critical it is. Or to put it another way, what are the consequences to human life in the event of a failure? There are 3 exposure categories that essentially describe the surrounding topography and therefore how the local wind loads are adjusted. For years, I wondered why there was no exposure category A. Basically, the committee that was determining exposure categories decided that a very heavily built up city center with tall buildings was too complicated to model, and that you would either do a wind tunnel study on your structure or just assume exposure category B. Signage is generally considered to fall under risk category 1 or risk category 2. Most people will classify a small to medium-sized freestanding sign as risk category 1, though the local codes department may feel otherwise. Large freestanding signs, or any medium-sized ones that are located near crowded areas, should probably be risk category 2. And though we're focused on freestanding signs, any sign that is attached to a building should be risk category 2 unless the building itself is a risk 3 or risk 4, an elevated higher criticality structure. So what about exposure categories? As mentioned before, the exposure category is a reflection of the topography and surrounding built environment. Essentially, it measures the ground's roughness. I'm summarizing this for our presentation, but you can see from the description on the slide what we as your engineers have to consider. Exposure category C can be considered the default setting, open terrain with scattered single-story structures. Exposure B is more built up, which disrupts the flow of the wind. Therefore, the wind load applied can be reduced. You can see in the slide, typical suburban area, lots of one single story with structures with scattered 2-story structures thrown in. This is another example of exposure category B, where you get into a more common downtown area with multiple story structures. And in the other direction, exposure category D increases the wind loads that are applied. Basically, exposure D conditions are on the edge of large flat areas and extend downward from that. Other than coastlines, it isn't terribly common, though you could run into this in the Midwest, and we've seen it several times in New Orleans based on the orientation of the site to the Mississippi River. An interesting thing about this aerial photograph of Houston and Galveston is that you can see all 3 exposure categories in one photograph. So if you look at the coastline down kind of in the lower right section of the photograph, that is exposure category D. Obviously, with the Gulf over there to the right, you've got a long unobstructed area, so the wind is at the highest wind pressure. And then as you move inland, you go to the upper left corner and you see the downtown part of Houston. That is clearly exposure category B, where you've got all the buildings and that's disrupting the wind flow. And so that's at the lowest wind pressure. And then in the middle, whether it's in the lower left or upper right corners where you've got very rural areas or some of those edge areas, you've got exposure category C, kind of that middle default wind pressure. So now we get into the analysis. What are the loads that are applied to a sign that your engineer needs to consider? Basically, 2 different types of loads. There's a dead load and a live load. A dead load could be considered a constant load that's not going to change, whereas a live load is variable. The most common form of dead load is just simply the weight of the sign structure itself. This is permanent and it doesn't change. Some of the live loads that need to be considered for sign structures, there are others that don't apply to sign structures, are wind, snow, and seismic loading. Wind load is simply the force that's applied to an object, in this case a sign, due to the wind, which pushes, pulls, and actually does both. Snow load is probably not going to be a factor unless your sign cabinet is wide and you get a lot of snow, or if you're looking at a project that is a canopy or an awning. And then seismic loading is, not surprisingly, due to earthquakes. Mainly, you will see that in California and Illinois, There are a few other areas. Memphis, seismic loading is significant, and there's some places along the Atlantic coast where seismic loading needs to be factored in. The wind loads, I've got listed up there 3 different ASCE design manuals. Those are different versions that track and map to the different versions of the building code. So your engineer will be familiar with those 3 versions. And then just to make you aware, there are special wind regions scattered throughout the United States, mainly in mountainous areas. Several of them are in Colorado, but the Smoky Mountains also have some special wind regions where you might have elevated wind pressures just due to the topography. All right, so let's talk about freestanding signs. We'll give an overview of some of the types and some of the things that your engineer will hopefully be considering. Admittedly, we're only touching the surface. And again, I'm not trying to make you an engineer. I just want to open the window a bit to help you better understand some of the design factors underlying your sign project. A lot of people use a lot of different names for signage. So I feel like it's important that, at least for the purpose of this discussion, we use the same terminology. First, a freestanding sign is not connected to anything else other than obviously to the ground. Here are some of the different types of freestanding signs. A directional sign points the way for pedestrians or drivers, and it can be especially useful when a business is not clearly seen from the entrance to a complex. The important thing about a directional sign, that name is not really referring to how it's constructed, but its usage. And as you know from signage codes, there may be certain allowances for directional signs that are different from monument or other freestanding signs. So again, the terminology is important so that you can maximize what's permitted for your site and take advantage of allowances for directional signs. A monument sign is simply a ground sign with a low overall height to width ratio and is solid to the ground. For these remaining 2, there really isn't agreement on the definitions, but for the purposes of this presentation, we'll go with the following. A pole sign is a freestanding sign with a visible support structure, and a pylon sign is a freestanding sign where the support structure is enclosed by a pole cover. So if you think about it, if you've got a pole cover, it's a pylon sign, and if the pole is exposed, it's a pole sign. So directional signs. This one is pretty small at 3 feet 10 inches tall, and by no means is it the smallest one that we have had to engineer. But in our experience, in high wind areas such as a lot of the coastal areas of Florida, and perhaps some of the other areas along the Gulf Coast, all signs need to be engineered. One of the things to pay attention to in a design like this is how is the sign itself connecting to the foundation. It's pretty common to direct embed the poles into the foundation, and that's a straightforward design. But if you're using embeds or anchor bolts, the spacing and depth of those embeds you may need to pay particular attention to. This is a pretty typical monument sign, but one question that comes immediately to our mind is that base CMU block or solid masonry, or is it a framed hollow base? In this particular case, it wasn't just the graphic. Yes, it was going to be solid CMU. And that factors into the analysis that we do and what type of foundation would be best. Because of the weight of the CMU block base, the way it's designed with a concrete pad and a round pier foundation is not the most cost-effective design. That concrete pad would need to be very thick to support the weight. In this case, a more cost-effective and labor-efficient foundation is a spread foundation. Your engineer will know enough about this to be able to help you decide which foundation is best if you have the luxury of having a choice and not constrained by site conditions. This is another monument sign that shows an interesting challenge that many people wouldn't consider. As you can see from the middle of that top graphic, the support pole in the middle of the cabinet is going to be anchored to the CMU base, which seems like a good idea and is certainly logical. It makes sense. except for one thing. Once we started laying out the design and placing the CMU blocks into that foundation, we realized that all 4 of those embed anchors are located in the same CMU block with 2 in each cell. Per the building code, we are only allowed to consider 1 anchor per cell. So this suggested design doesn't work. Instead, we came up with an approach where a short stub was installed from the top of the foundation to the top of the CMU block base. And then the cabinet pipe itself was connected to the match plate. Problem solved. Again, I like to use this example because working with an engineer who actually understands what you're trying to accomplish, they won't just analyze the drawing and just give it back to you. They'll think in terms of what does code allow and make sure that what you're proposing to do actually will get approved in the event that an inspector shows up and starts to question things. Moving to freestanding signs. In this case, this is a pole sign because it's freestanding with an invisible support structure. This actually shows something that we'll touch a little bit more later, where we're adding a new cabinet to an existing structure, but there's some common themes to new and existing pole signs that should be considered. One is, what length are the pipe stages? Are there certain limitations? We were having a conversation with a client yesterday about different pipe lengths and what is transportable to the site and their general preferences. And so there may be constraints as to what's you can actually get to the site and install. There may be constraints as to what's available. You may have something back in your boneyard that you can use, or there may be limitations on what you can buy. So that kind of information needs to be factored in. Another big question to consider with a pole sign is, what type of foundation can you or will you use? We'll talk about this in a little bit, but round pier, spread footer, lateral wall, those all have different implications and may be constrained by the site or the geology of the site as to what you can use. Another thing to communicate to your engineer is, how will the cabinet mount to the pole? In this case, you've actually got 2 different. You've got the secondary sign, the mainstay suites, that is going to be, well, actually, they're both attached the same way. Now that I'm thinking about it, they both saddle mount, where they just sleeve over the pipe and are connected to the pipe internally that way, as opposed to having a mounting plate. But your engineer needs to know that so they can properly design things and prepare the drawings based on what you need. This is another example of a pole sign. It's a little bit hard to tell from the scale, but I like to show this one because this topped out at about 130 feet tall. That base stage of pipe is 8 feet in diameter, and you have a massive spread foundation. It's approximately 27 feet by 32 feet by about 8 feet thick. The loading on this sign is huge, and the future plans for the sign were also to put a tertiary cabinet up on the top. Everything can be analyzed, and it's really fun doing something of this scale, but this just shows the magnitude of what a freestanding sign can be. This is an example of a pylon sign, which again is a freestanding sign that has an enclosed support structure. The client actually referred to this as a monolith sign. Some people would call it a monument sign. Different people call it different things. But one of the things that quickly became a point of concern for the design of this was the actual framing of the cabinet itself. It's large enough that you might need to verify, or you might be required to verify, that the frame works out. Roughly 600 square feet of cabinet. And so all that framing is receiving a pretty significant wind load. And so we did an analysis of this to make sure that it wouldn't buckle under the wind conditions and take care of our client by watching that for them. But if framing is not an issue, it gets very simple. It's just a support pole directly embedded into a round pier foundation. And because it's all framed, you don't have to worry about the weight of the frame needing a pad underneath it. So it's just round pier with the direct embed pole. Freestanding signs can get pretty interesting. Architecturally, this gateway sign that we designed looks really good, but once we got into analysis, we realized that there were some issues as to how the load of that center sign is transferred through the vertical support poles. Engineers always get accused of over-engineering things, or often we get accused of over-engineering things. And so when we realized this, the first thing we wanted to communicate to the client was that approximately 85% of the load of those signs is going through the center poles, those two innermost poles. And so only 15% of the load is being transferred through the middle and outer poles. If you wanted to just have a very cost-effective sign, you would actually reduce the diameters of those center and outer poles, and it would result in a cost savings. Except a design like this is obviously visually important to the client and to the architect. We talked with our client, we presented that information to them, and not surprisingly, they wanted to keep those center and outer poles the same diameter as the inner because the look and feel of the sign was particularly important. It's a beautiful sign. And again, as our client's engineer, we wanted to communicate concerns and questions that we had just to make sure that they were thinking through everything and they wound up with a good design. As shown here by the structure that we engineered in Detroit, the possibilities of freestanding signage are endless and can be in them of themselves very complicated architectural elements. In addition to the foundation, we prepared framing drawings for this golden ring. It was about 25 feet in diameter. It turned out to be a very complicated 3D structure. Each frame section, all the panels and all the internal frames were different. To ensure that we designed a safe structure, we utilized a 3D finite element analysis software package to model and check to ensure that all the structural components were strong and that the deflection under full wind loading conditions was minimal. It was important that the fit and finish of these panels be of high priority because you didn't want the sign or the structure deflecting and creating gaps in those panels. Want to talk about the designs a little bit, get back into the engineering piece. This is an image from a great book that gives a good overview of signage designs, which I highly recommend. It's titled Sign Engineering Structures, and it's written by Ben Jones. It's a bit older, so it's a little out of date, but the fundamentals are tried and true, and it's really good information. The image on the left shows how the dead load acts on a sign structure. Not surprisingly, because of gravity, the weight of the structure is pressing down. So that's vertical movement from the dead load or the weight of the sign structure. The image on the right shows the wind load. It's moving in a side-to-side manner. The wind presses on the face of the sign cabinet and on a pole, and it tries to rotate around the base of the cabinet. That creates a moment, a rotational movement for the sign. And as you can guess from this diagram showing seismic loading, seismic analysis gets pretty complicated, but depending on your region, it may be necessary. Your engineer will analyze the structure and determine the seismic loading and compare that to the wind loading in various load combinations. Whichever is the largest combination controls. Seismic loading is driven by the total dead load or the weight of the structure. Most of the time we see that wind load controls, unless you have a medium to large freestanding sign, depending on the weight of it, seismic sometimes will control. One thing I like to mention is frost heave. Pay attention to foundation depths. We don't run into it too much in the South in our region, but if you have a project that's getting up into the upper Midwest or New England or some areas, you can have a pretty deep frost line. So frost heave, if you're not familiar with it, is a principle where the moisture in the soil freezes, and that freezing causes the soil itself to expand. If you've got a monument sign, a great example is a monument sign. So if you've got it and it's shallow, the foundation is shallow, just because from an engineering point of view, it didn't need to be too deep. So say it's 2 feet deep. and you're up in mid to northern Kentucky, and you've got a 36-inch frost line. So the soil can freeze to a depth of 3 feet. If you have one of those really cold winters, if it freezes, you can have the differential expansion of the soil such that the monument sign tilts, the foundation actually tilts, and that can create instability for your sign. Talk a little bit about foundation types. 3 general types: round pier, spread, and lateral walls. A round pier footing, some people call it an augured footing, is drilled into undisturbed soil. Sometimes people call a round pier footing a direct embed, but technically direct embed is the term used when the pole itself is embedded into the concrete in lieu of using anchor bolts and rebar. It is important to make sure you use correct verbiage. A caisson foundation is technically a different type. It's a subset of round pier foundations. A caisson foundation is constructed at the surface and sunk to the desired depth, as opposed to a true round pier foundation, which is drilled and it's a void that you fill up. You typically will see caisson foundations in water, maybe for a pier or for a bridge or something that's being installed in water, so that it's constructed on the surface and lowered to depth. Speaking of round pier foundations, please don't insert sonotubes or similar products into the ground and leave them there. Pier foundations work through the interaction of the sidewalls with the soil, and that tube, since it's a fibrous material, will eventually degrade, leaving a gap between the concrete foundation and the surrounding soil, which will significantly weaken the foundation against overturning. A spread foundation is basically a block that's laid on its side, a block of concrete laid on its side, and a lateral wall foundation is basically a block of concrete that is standing upright on edge. This is about as simple as it gets: 2 support poles directly embedded into round pier foundations. This approach, round pier foundations, seems to be the #1 choice in Texas. The other day, we were speaking with a client about a site, and in that case, it was a large interstate sign, and the foundation was going to be approximately 8-foot diameter and over 50-foot deep, and they didn't even blink an eye. This is still a round pier foundation, but in this case, you have anchor bolts. Sometimes people refer to them as a specific type, which is called a J-bolt, with a cage of rebar inside the foundation. And I want to make sure and emphasize that point. There always needs to be that rebar inside the foundation when you're using anchor bolts. Concrete by itself, excuse me, does not have the strength to resist the overturning moment of a sign that is anchor bolted to the foundation. Typically, we see this when someone's not wanting to have the support pole be directly embedded into a deep foundation. For example, you have a large round pier foundation, and as expensive as steel is these days, you may not want to have 20 or 30 feet of pole buried inside the foundation. Excuse me. Other times, people just prefer it this way. Maybe the pole will be replaced in the future, or maybe it's just a preference. This is an example of a spread footing, which, as I mentioned, is a block of reinforced concrete that is essentially laid on its side. A standard efficient design has the foundation longer in the direction of overturning, perpendicular to the sign face. So if you look at the structure profile over on the right, that direction, the 7-foot 6-inch direction, is the direction of overturning. Typically, that is longer. But in this case, the masonry surround and base at the base of that sign requires a width that is greater than the masonry. So as you can see, it is wider than it is longer. So I like to use this as an example where it's a little bit counterintuitive to what you would expect, even though there is good reason and good engineering practice as to why it is this way. Often a lateral wall foundation is used if you need a wide foundation for the concrete or a masonry base, but if you don't have the area for a spread foundation. Typically, you can install this with a backhoe or a track hoe. We see this a lot of times in parking lot islands or edges of properties where you have a lot of utilities and you really have a limited amount of area available for a sign. And so you just need to slide it in between some fairly tight restrictions. It is a more complicated type of foundation to install, and so complicated usually equals more cost, but given your site constraints, this may be the best solution or the only solution that works. And what about existing signs? One of our clients sent us this photograph and asked if this structure can be used. They didn't have any information about the foundations or original sign cabinets. We were able to reverse engineer for them what could be done to use this sign structure. A good engineer familiar with signage can figure it out for you and help you solve your client's problems. We'll talk about this a little bit more in the following sections of the webinar. But a few things to keep in mind is that the International Building Code does have a section relating to the reuse of existing buildings. So reusing existing sign structures. It's a very powerful tool, but there are limitations to it. One of the most obvious is that you cannot increase the loading more than 10%. The other is that it's a little bit vague, but you have to determine if the structure is in good condition. A sign structure inspection is key for doing that. It's always good to see if you can find out anything about the foundation. Sometimes you can, sometimes you can't. Sign structure inspections are the key to determining whether the sign is itself in good condition. We've got a good process. We're going to go over this in depth, but gathering information about the sign, the poles, everything that you can and what condition it is essential. And as a refresher, what makes a good sign order? The information that is needed includes things like the dimensions of the sign that you want to have engineered. If it's made of unusual material, what is the weight? We do a lot of work for Cracker Barrel. Most people in the South are familiar with their signs. Their sign faces are typically made of porcelain panels. Those are very heavy. And so that weight actually is taken into account rather than just using the standard rules of thumb. We know the specific weights of those panels and factor that into the design of the freestanding signs. Do you have a preference for anchor bolts or direct embed the pole? What about the foundation? Some people do have a preference. They like a certain style, or even limitations as to if you're doing a round pier foundation. Do you have a limit as to the size of the auger that's available? You may need to limit it to a 36-inch or 42-inch or whatever is available for you. How will the cabinet be attached to the pole? That, again, whether it's going to be a saddle mount or mounting plate is important so that that gets engineered as part of this permitting process and design process for you. Other information that can be helpful to your engineer. I've listed a few things, but the third and the fourth bullet points are particularly important. Undisturbed soil versus backfill. If this sign is being installed at a new site, say some developers come in and they've got this new development there, it's quite possible that they may have backfilled to even out some of the surface irregularities. Unless backfilled soil has been compacted to a certain standard and tested such that the backfill compaction is verified, it cannot be considered as soil when you're installing the sign foundation. So if you've got 4 feet of backfill and before you get to undisturbed soil, that entire 4 feet has to be disregarded as far as the foundation depth and installation of the foundation. So a lot of times a geotechnical report isn't available, especially if it's at an existing site. But if you can get that information, that helps your engineer to know about backfilled soil or not. And also if there are any particular soil properties that are advantageous. If we don't know that information, we have to assume the most conservative values for the soil. And so the more site-specific information we can get, typically the better the design will be, which means it'll be more cost-effective for you. This is an example of a request and order form, actually, that a client of ours sends to us. And I like to use this as an example because it summarizes everything very well. They've got a zip file that's attached to the email that includes artwork for the signs, the geotechnical report. Sometimes they'll have building survey information, photographs, all the information about the site. They send as much as they've got on the front end. And if you look at the email, one of the things that's in the middle of the email that a lot of people forget is the site address. That is very helpful for us because depending on where the sign is going to be installed, the building code may change depending on the address. And in particular, the wind speed could change. An example that comes to mind is the Tampa, St. Petersburg area. There are 3 different wind zones across the city. So if we don't know the street, or depending on how close it is to the edge of those zones, sometimes even the physical address on that street, the actual building number, we don't know which wind speed needs to be used. And so we'll always go with the most conservative to make sure that everything is covered, but often more conservative means a little bit oversized, and that could mean additional cost. Well, if that was an example of a good sign order, what is a, shall we say, less than helpful sign order? We have received emails that have no address for the site, including a city or a state, no contact information from the client, and a graphic with no dimensions of the sign. Those make it really difficult to do any kind of proposal, much less any kind of engineering. Or slightly less difficult, but frankly, sometimes more fun. This is what we installed, and now the city is requiring a permit. Can you figure out and see if this works or not? On this slide, we've got an example of a checklist we'd be happy to send you that summarizes most of the information that your engineer would like to know. We can't capture every situation in this form, but it does get most of them. If we don't get this information, we can usually make the design work out, but more information is always better and helps us to optimize the design, which results in a more cost-effective construction project for you. I want to take a quick look at calculations. I know a lot of times you're getting the engineering simply because permitting requires it, and you may even be working with a local sub that doesn't actually look at the drawings before doing the installation. So I want to point out a few things on a recent project that we did, both drawings and calculations, and kind of point out why you would want to at least review these drawings. In the upper left corner, I've got circled the diameter and grade of the bolts. That A307 material for the bolts is essential because our analysis is based on the grade of metal that is used in the bolts. So if you get a lesser grade of bolt, it may not actually engineer out. And so you may create a weakness in the sign structure that, because engineering drawings weren't followed, could result in liability if a failure were to happen. In the lower right corner, you can see the rebar and the way it's laid out, evenly spaced, and the sizing and the number of the rebar. Obviously, you want to follow that. It's not circled, but if you look at detail 1 in the middle, that you can see the pipe with I call them feet on the bottom of the pipe. There are different ways to support the pole off the bottom of the foundation. But what's important to know about that is that if the pole is just put on the bottom of the foundation, the weight of the pole will press through into the soil that underlies the concrete, underlies the foundation. That metal to soil interface creates corrosion. There's the electropotential difference between metal and soil causes corrosion. And so by having those feet, it does 2 things. One is it gets the foundation, the pole up off the bottom of the foundation so that you don't have that soil interface. But secondly, and equally important, it allows the concrete that is you're pouring the concrete in the foundation, it allows the concrete to flow up into the base of the pipe. And it really helps to lock the pole in place so that it won't wiggle or wobble or go anywhere. On these calculations, I've reviewed a lot of engineers' calculations, and we all do things differently. How we present the calculations all have essentially the same approach. We do, some engineers include the calculations actually on the drawings themselves. We do ours as a separate package because sometimes you don't have to submit this information and it's just easier to have the drawings. And so I know this part is a little bit unique to the way Elrod does things, but this information will show up in whichever engineer you use. On the left of the screen, this is where we're analyzing the pole, and you can see that number circled, 84.7%. What that's telling is that we're comparing the forces that are applied to the pole versus the allowable maximum stress that can be applied to the pole. That's not the ultimate stress, and that's a rabbit hole we don't want to go down right now, but the allowable stress. So you're seeing at 85% of capacity, that's really in a good spot because you don't want to run up against 99.9% of the capacity because there's no margin for error. But somewhere in the mid 80s to low 90s, that's really a good place to be when you can. If you look at the sheet on the right, that's a match plate. Really just pointing that out to say, if you ever wanted to, you can track the engineer's calculation to make sure that all the numbers tie together, and you can kind of see the flow of thinking and the flow of analysis. Just if you ever, like I said, if you're ever bored and you want to follow how the engineer's doing their analysis. This sheet shows two things. The sheet on the right is a spread foundation. So you can see in this case, it's actually a square type where 8 feet 3 inches by 8 feet by 3 inches by 3 foot thick. But again, just kind of showing the flow of the information and where we get our analysis results that we then turn into the drawings. The center screen and the right sheet are from the wind load analysis that we do. So again, this is a lot of detail that you aren't necessarily wanting to know about, but just to communicating that this information all flows through, it's all trackable and all transparent and should be reviewed if you ever wanted to, or if the permitter wants to see it. Lastly, this is just an example of a round pier foundation. Up at the top, you can see the loads that are applied. And then you can see in that lower circle, you've got a 2 foot diameter, 5 foot 10 inch deep, and just how everything is checking out on that. But that's just communicating the information for you. All right, so let's talk about existing sign structure inspections. What is the point of an existing sign structure inspection? You've got an existing sign, somebody wants to put a new cabinet on it, they want to swap out the existing one, or they want to add another cabinet to it. And so you need to determine, can that structure handle this additional load or the new load, or was it even designed properly to begin with? No one wants to see this. Instead, this is what you want to see. This photograph was sent to us from a sign company conducting surveys after an EF4 tornado hit Ringgold, Georgia a few years ago. What I like about this photograph is that you can pretty much see every form of sign failure in the foreground and one large sign in the background that didn't fail. Okay, maybe you could consider 2 signs that didn't fail if you look at the one towards the right side where the faces blew out. But yeah, technically that didn't fail, but it didn't successfully survive. I don't want to press this point too hard, but this is an extreme example of what can happen when signs are designed based on experience versus being designed to code. But seriously, what's the point of a sign structure inspection? Public safety is always number one. An inspection program can prolong the asset life for your clients. It may actually result in you turning a one-time project for a client into a recurring business model. And then thirdly, I want to use an example from our experience to show the benefits of a sign structure inspection program. Public safety. As you know, many large sign structures are located near the public, and anytime a structure fails is bad. When it fails and someone is injured or there's a fatality, it's just terrible. It's a tragic event. And so anything that could be done to avoid these losses to human life is always worthwhile. As I mentioned, prolonging the asset life for your client may be a path to selling a recurring revenue situation to your clients. High-rise signs, it's no surprise, that's a significant capital expenditure. We were looking at one the other day that was over 150 feet tall, and it was numbers that I was hearing were over $1 million for the sign structure, which is a huge amount of money. And I have a hard time imagining how someone justifies the return on investment for that, but they are still moving forward, and that's going to be really cool when it's done. But another question that's actually never been answered: what is the average life of a high-rise sign? A well-maintained sign can last much longer than any of us will be in the career. And by prolonging that asset life, you're reducing the capital expenditure requirements for your client. What would it mean to your client if you could double the life of that sign? And as I mentioned, I want to give a case study example. One of our clients has several hundred locations, approximately 700, and they asked us to review and analyze sign failures that they had experienced. In their history, they have had 4 sign failures. One was due to a tornado in Oklahoma City, in which the highest wind speed on Earth was recorded. The wind gauge itself broke at 305 miles per hour, so no one actually knows what the ultimate wind speed was at the site. You can't cost effectively design for a wind speed of over 300 miles an hour. But interestingly, the other 3 sign failures were due to installation issues, mounting plates that weren't welded to the pole, missing mounting plate bolts, etc. So a good installation is vital, and a repair and inspection program would have prevented 3 of those sign failures. So what are the primary components of a good sign inspection? A detailed scope prepared in advance, providing information about the structure, overall diagram, detailed diagrams. One of the things that we've learned is that a list of pictures is critical in order to communicate the information and gather the information that you need. And we've also learned that making it as easy to follow and as standardized as possible is a real benefit. Particularly on a high-rise sign, you've got a crew out on the site, and they're up in a bucket. It may be over 100 feet up in the air. The last thing they need to be worried about is, did they follow the directions and did they capture everything? It needs to be as standard as possible to make it as easy so that they can focus on being safe and getting their work done. This shows two pages from our sign structure inspection form. The page on the left, the cover page, is just a general overview of everything that's going to be done. And then on the right, that's typically the next page. We always include either a photograph or a diagram of a sign and point out everything where we need measurements, wall thicknesses, heights, lengths, all that information. So again, with having blanks to fill in, we want to make it as easy as possible for the folks in the field to gather this information. On the left, you'll see a list of photographs. It looks exhaustive. It is exhaustive because, again, we've learned by doing these over the past 30 years, the more we spell out what needs to be done, the less likely something is going to be forgotten. On the right is just a typical detail where we need measurements on the multi-stage splice. A lot of the ones we do for one of our clients are signs that we designed, but what's designed isn't necessarily what goes into the field. There may be variations on wall thicknesses or heights, information like that. So we always want to gather accurate in the field information, even if we designed the sign several years ago, just to make sure that our analysis is accurate. All 4 people represented on this slide are essential team members for the project. Obviously, the sign company, y'all have got the project. It's your primary client, your primary role, the sign company also provides the manpower to inspect the sign. Anytime you have a multi-stage structure or otherwise a structure that has welds, a certified welding inspector is going to inspect and test all the welds to make sure that they're still in good condition. You need the engineer to review that information, analyze the structure to make sure it's safe and in good condition. And having a client that is involved and engaged in the process is, again, essential to making this a smooth and productive project. So what needs to be inspected? Essentially, everything top to bottom. I want to show some inspection photos. These are all from projects that we've done where we did an inspection. Here, we're starting out at the cabinet. You can see in the left, holes in the top of the cabinet lead to water penetration, which leads to rust, which can lead to a structural failure. On the right, the peeling vinyl, that's not a structural problem, but particularly if your client has multiple locations, they may not be on site every day. They may not realize that the sign itself is starting to fall apart. And so sometimes it's a quality issue that they want to make sure that the look is still good, because if you have a shabby sign, that may communicate that that shabby work happens at your client site. And so when we're doing a structural inspection, we don't just gather structural information, we gather other information about the sign itself and communicate that to the client so that they can stay on top of things. Looking inside the cabinet, this is a tertiary steel member that's supporting the framing of the cabinet. And what you can see in this, particularly if you look in the center, is actual section loss of that framing member. The rust is actually eating through the metal, significantly weakening that structural member. Another interior cabinet photograph. Algae in and of itself isn't necessarily a bad thing, but it is indicative not only of water penetrating the cabinet, but also water that stays inside the cabinet, creating a very humid and damp environment. This will eventually lead to rust and structural damage to the cabinet itself. Moving down the sign, this is the mounting plate. This is an example of material degradation of the mounting plate. We caught it early enough that the solution to this would be simply to grind down to bare metal, coat with a rust prevention such as Por 15, and then repaint. In that case, you're actually stopping the rust. But if you don't clean it, if you don't treat it, if you don't prevent future rust, this will continue eating away at the meat of the mounting plate, potentially weakening those bolted connections once enough is degraded. If a sign has got external lighting, the light arms are sometimes one of the more critical and overlooked failure points for a sign structure. You need to look at those joints, especially at the bends where the metal comes together, and make sure you don't have any rust of those welds. Our inspection program actually started when a light arm fell off a sign one night and landed in the parking lot to be discovered the next morning. Fortunately, nothing was hit, but those light arms weighed over 100 pounds each and would have done a lot of damage had they fallen on something. Multi-stage splice welds. The photograph on the left shows really good inspection notification and information. When we do an inspection, we're not actually on site as engineers. We're relying on the sign company and the CWI to communicate and gather that information for us. And so as you can see, the splice welds, the slot welds, the indicators that were found in the weld, all that stuff is marked with a grease pencil. And the photograph is from enough distance that we can actually see what is there and how things are oriented. If someone just takes a picture of a slot weld and it's a zoomed close-up picture of the slot weld and it's not identified, that's nice, but that's not really very helpful because we can't tell where that is in relation to the sign. And that does matter when we're doing our analysis. So this notation, it was really good notation. The photograph on the right, you're showing a bolt that was welded into a lift hole. That's not an acceptable technique for filling a weld hole. it still does allow the chance for water to get into the inside of the pipe. And so number one, it wouldn't pass the AWS standard for welds. But then secondly, you are creating a pathway for water penetration to the interior of the pole. And you want to prevent that as much as possible. This is another example of a splice weld where you can see the majority of the lower weld kind of at the bottom of that rain cap is missing. And that creates a significant weak point in the sign because you don't have a good connection between the upper stage and the lower stage. In this photograph of slot welds, you can see that the inner compression ring from this upper pole stage is not connected to the lower pole pipe stage at all. You've just got those slots. The slots are there, but there's no weld. And because there's no weld, that inner pipe is not connected to the outer pipe. So the stresses that come from the upper stage of the sign are not being transferred efficiently to the lower pipe. And by not transferring efficiently, that means you're creating added stress at other locations, which is giving a higher chance of failure of the sign structure. Not only in this photograph are there no slot welds, but there don't appear to be any compression rings on that upper stage pipe at all. And in this case, not only do you not have a good load transfer, so you've got load concentrations happening, but if there truly aren't intercompression rings, there's too much freedom of movement of that upper pipe stage, and that creates a significant amount of stress on the connection at the rain cap. There's too much freedom of movement for that inner pipe stage. Down at the bottom, you can see these anchor bolts. Two things of note from that. Grout needs to fill the entirety underneath the pole so that you can help distribute the load, but also the anchor bolts themselves need to penetrate at least 2 threads out of the bolts. There's a real challenge to fixing this one here. The grout would be easy to fill in and replace, but actually fixing a situation of where the double nuts aren't fully engaged is a weaker connection. And so that it can be fixed and repaired, but this is a challenging one. Here, we've exposed on all of our inspections, we request that at least the first time an inspection is done, that the base pole be exposed from the top of the surface down to the top of the foundation. What you can see here is some pitting in the base pole that it was due either to the interaction of the soil and the pipe, that galvanic corrosion that we talked about earlier, or this was also located in a landscaped area at our client site. And so just having a constantly wet area because of the sprinklered landscaping created a more corrosive environment. If this pitting is not stopped, you're going to see a significant weakening of the pipe right there at the soil interface, almost the point of maximum stress of the sign. And again, that could lead to a catastrophic failure. In this case, we caught it early enough that we were able to repair it on site, and in the field. And so the structure is safe and didn't need to be replaced, but it did need to be observed and noted. Sometimes you just don't know what you'll find. That photograph on the left, I was actually at an adjacent site doing an inspection, and I turned around and saw that. And I honestly don't know what's going on. It almost looks like there's a spiral cut where they tried to stick something in between 2 sections of the pipe, and the weld is almost completely broken all the way around. Fortunately, a few years after this picture was taken, they tore that site down, and that's not a problem anymore. The one on the right was from an inspection that we did on a client site where they had an adjacent landowner ask them if they could put a secondary cabinet on the sign after it was installed. Our client said, sure. When we came out to do the inspection, we took the secondary cabinet off to look at the pole. Turns out they not only had they put their secondary cabinet on, but they cut the pole, put in a smaller diameter pole, welded things back up, and put their cabinet back in place. Obviously, that is not per design. That is significantly overstressed. Fortunately, nothing happened to it, but it was fixed and taken care of, and it's a much safer structure now. So once you have the data, what now? You work with the engineer, they review the information, they analyze it, and they make any recommendations for repairs, if any recommendations are needed. Why do you use a PE? One of the things that it does is it brings third-party objectivity to it. You don't want your client questioning, are the repairs necessary? Because, well, you just don't want them questioning that, because having an engineer review it, when an engineer puts their seal on a document, they're legally responsible and liable for that report. So that just gives your clients a little more assurance that things truly are necessary that are being recommended. One last thing I like to point out, someone's always watching what you're doing, so be careful and do good work. In conclusion, hopefully this has explained a bit about what engineering goes into your sign and what your engineer needs to know to give you a good design. Sign engineering can be relatively straightforward, but as you've seen, there's still some complexity to it. And if your engineer doesn't want to know this information that we've discussed, it may be time to reach out to someone else. And there are several very good sign engineers out there. Thank you very much for your time today. Please reach out if we can answer any questions that you might have. We do love this stuff.